The equation E equals mc², formulated by Albert Einstein as part of his theory of special relativity, expresses the relationship between energy, mass, and the speed of light. Here's a breakdown. E represents energy, measured in joules, m represents mass, measured in kilograms, and c is the speed of light in a vacuum, approximately 299,792,458 meters per second. The equation reveals that mass and energy are interchangeable. It shows that mass can be converted into energy and vice versa. They are not separate entities but two forms of the same thing. Speed of light squared. The c² term, which is a very large number, acts as a conversion factor, indicating that a small amount of mass can be converted into a vast amount of energy. Real-life applications and examples of E equals mc². Nuclear energy, nuclear fission. In nuclear power plants, the nucleus of a heavy atom, like uranium-235, splits into smaller nuclei. A small amount of the mass is converted into energy, producing immense power, nuclear fusion. In stars, including our Sun, hydrogen nuclei fuse to form helium, releasing energy as mass is lost during the process. This is why the Sun shines. Atomic bombs. The destructive power of atomic bombs comes from converting a small amount of mass into energy via nuclear fission or fusion. For example, in the Hiroshima bomb, only about 1 gram of matter was converted into the energy that caused widespread destruction. Particle accelerators. High-energy physics experiments, like those at CERN, use particle accelerators to study subatomic particles. When particles collide at high speeds, the energy from the collision can create new particles, demonstrating the mass-energy equivalence. Medical applications. PET scans. Positron emission tomography, or PT scans, rely on the principle of mass-energy equivalence. Radioactive isotopes emit positrons, which then annihilate with electrons, converting their mass into gamma rays used to create images of the body. Star life cycle. When stars collapse into black holes or explode as supernovae, a significant amount of their mass is converted into energy. This process is observable as light and radiation across the universe. Even in chemical reactions, though imperceptibly small, a tiny amount of mass is converted into energy. This energy is released as heat, light, or other forms. Imagine you burn a piece of paper. While it seems like only chemical reactions are happening, at the atomic level, a minuscule fraction of the mass is converted into energy in the form of heat and light. The conversion rate is so small that it's nearly negligible in everyday life. But in nuclear reactions, the scale of this conversion is far more significant, making the concept of E equals mc² highly impactful. This equation fundamentally changed how we understand the universe, highlighting that energy and mass are two sides of the same coin. Einstein's law of energy and mass, encapsulated in the equation E equals mc², provides a profound understanding of how energy and mass are related. This law explains that a small amount of mass can be transformed into an enormous amount of energy, and vice versa, depending on the situation. Here's a detailed breakdown of how this law applies to real-life problem solving. Energy and mass. Relationship. Mass is not just stuff. It is a concentrated form of energy. When mass is converted to energy, the energy released is proportional to the mass, multiplied by the square of the speed of light. Since the speed of light is an incredibly large number, even a tiny amount of mass can produce an enormous amount of energy. Real-life problem-solving applications. Nuclear power plants. Clean energy. The problem. How can we produce energy efficiently to meet global energy demands while reducing greenhouse gas emissions? The solution using E equals mc². Nuclear fission in power plants splits heavy nuclei, like uranium or plutonium, causing a small amount of mass to be converted into vast amounts of energy. For example, 1 kilogram of uranium-235 can release approximately 18 million kilowatt-hours of energy, enough to power a city for days. This is far more efficient than burning fossil fuels. Medical imaging, specifically PET scans, poses an interesting challenge. How can we non-invasively visualize internal organs or detect cancer in its early stages? Well, PT, or positron emission tomography, scans use radioactive isotopes that emit positrons. When a positron meets an electron in the body, their masses annihilate, converting into gamma-ray energy, or photons, that are detectable by the scanner. This precise imaging technique helps doctors locate tumors and assess organ function. Nuclear weapons and understanding their destructive power is a critical issue. So, how can the energy yield of a nuclear explosion be predicted? In an atomic bomb, nuclear fission or fusion reactions convert a tiny amount of mass into explosive energy. For instance, the bomb dropped on Hiroshima converted just 1 gram of mass into energy, releasing the equivalent of 15,000 tons of TNT. This starkly demonstrates the destructive potential of mass energy conversion. Solar energy, or star power, is fundamental to life on Earth. But how does the sun generate the energy that supports life here? In the sun, hydrogen nuclei fuse into helium through nuclear fusion. A small fraction of the mass of the hydrogen atoms is converted into energy. Every single second, the sun converts about 4.2 million tons of mass into energy, which radiates as sunlight, providing the heat and light necessary for life on our planet. Space travel has always faced the challenge of achieving efficient propulsion for exploration. So how can we, overcome this problem? Well, one potential solution lies in the famous equation E equals mc². Future spacecraft may harness the power of matter-antimatter reactions for propulsion. When matter and antimatter collide, all their mass converts into energy, making it an incredibly efficient fuel source. To put it into perspective, just 1 gram of matter annihilated with 1 gram of antimatter would produce energy equivalent to 43,000 tons of TNT. It's like mind-blowing how much energy that is. Star explosions, or supernovae, are among the most spectacular events in the universe. But what causes the extreme brightness and energy release in these explosions? Well, when a massive star collapses at the end of its life, a portion of its mass is converted into energy. This release of energy is so immense that it can outshine an entire galaxy for a short time. Additionally, this process spreads heavier elements, like gold and uranium, into space, which later form new stars and planets. Let's think about everyday energy releases. How does mass energy equivalence affect processes like chemical reactions? In chemical reactions, the mass lost is tiny but measurable. For instance, when you burn 1 kilogram of coal, it releases energy, and the total mass of the products, such as ashes and gases, is slightly less than the initial reactants. The missing mass converts into energy, albeit at a microscopic level. To simplify this concept, imagine a paperclip weighing 1 gram. If you could completely convert that 1 gram into energy using E equals mc², the energy released would be approximately 9 times 10 to the 13th joules. This is equivalent to the energy produced by burning 3 million liters of gasoline. The key takeaway here is that Einstein's law of energy and mass is not just a theoretical concept. It has revolutionized our understanding of energy production, medical technology, space exploration, and even the origins of the universe. Its applications demonstrate how a profound scientific principle can solve real-world problems and advance human knowledge.